Greetings all. I, Prasanna, and my colleague Ruiming Zhu would be presenting a research review on the report titled Efficient Tandem Solar Cells with Solution Process Perovskite on Textured Crystalline Silicon, published by Hugh E. Michel Libestiani, and other colleagues. So we would first go through a brief abstract, and then we would move on to previous works in the realm of tandem solar cells. Then we would move on to some of the strategies and mechanisms employed by Hugh and his colleagues in tandem solar cells, and then we would move on to conclusions and further scope for improvement. And now I would like to ask Raymond to take over.
Thank you, Prasanna. Now I will talk about the background knowledge related to this paper. So perovskite solar cells have been in great interest in photovoltaic applications because they are relatively inexpensive. They have a tunable bandgap, they are easy to manufacture, and they have higher efficiency compared to some conventional solar cells. However, these perovskite cells are still facing some challenges. They are unable to overcome the single junction efficiency limit, and they may face quick degradation and complete breakdown when exposed to extreme conditions. So to boost the efficiency and stability of variable fabrication characteristics, tandem cell with solution process perovskite top cell layer were proposed as a potential solution to facilitate commercial application of these solar cells. So what exactly is tandem cell? Tandem cell are solar cells that have two or more cells stacked on top of each other with an interconnecting conductive layer. The tandem cell voltage and efficiency are generally higher than individual cells, with a potential efficiency over 30%. But these cells are not used commercially currently because it is difficult to obtain a current matching between different individual cells. Tandem cell with a perovskite top cell and a lower bandgap fully textured crystalline silicon bottom cell have a rising popularity because they can efficiently reduce thermalization losses and have a relatively uncomplicated tandem integration. Specifically, the fully textured bottom cell has an attractive efficiency potential and an efficient light trapping ability. And normally, these cells are made by a complex co-evaporation techniques, which is one type of physical vapor deposition processing, and it can be used to improve the quality of perovskite cells. However, precise control is required over deposition process during the evaporation process. Now I will talk about some previous work on tandem solar cell development. Sally developed a PVD strategy that enables top perovskite cell growth on bottom silicon cell. The co-evaporation of lead iodide and cesium borate created a perovskite top cell that can fully cover the bottom cell. And the pyramidal structure of bottom cell can be maintained even after the top cell deposition process. And this particular device can achieve a steady state efficiency of more than 25%. Other than physical vapor deposition processing, Fan in 2017 applied a solution processing to deposit perovskite top cell onto silicon bottom cell. In their work, the silicon bottom cell was pre-processed into a smooth surface, and using solution processing techniques, silicon bottom cell can also be fully covered by the top cell. The cost and time needed in solution processing is much lower than PVD, and the device still achieves a steady state efficiency over 20%. But early solution processing work, including Fan's work method, still suffers from inefficient charge collection and shunt path problems. Now I will hand over to Prasanna to talk about strategies and mechanisms.
Thank you, Raymond. To overcome the technical difficulties mentioned by Raymond, who and his colleagues demonstrated a unique method to deposit high-quality solution processed perovskite cells over the pyramidal textured bottom silicon solar cells. These wide band gap perovskite layers enhance charge carrier collection and considerably reduce shunt paths and manufacturing costs. In addition, they did not leave any uncovered silicon pyramids as observed during the physical vapor deposition of these perovskite layers. A relatively thick perovskite layer was employed in order to significantly increase the short circuit current density, to retain the curvature of the textured silicon surface, and to eliminate the need for subsequent flattening processes. One of the most integral methods to improve the device performance has been the surface passivation techniques, but this significantly reduces the carrier diffusion length. These techniques were not compatible with the rough surfaces of the perovskite layers generated because of the underlying texture present in crystalline silicon. Therefore, the carrier diffusion length within grains as well as within grain boundaries was increased by introducing a self-limiting passivant to the top layer, also referred to as self-limiting passivation treatment. This significantly improves the device performance by inhibiting phase segregation, by maintaining stability and orientation of perovskite irrespective of treatment times, and by enhancing carrier lifetimes as compared to other processes. So here are some of the images. Images A and B correspond to the top view SEM images of crystalline silicon bottom solar cells and the perovskite layer over these silicon pyramids. Images C and D correspond to the cross-sectional SEM images of crystalline silicon pyramids and the perovskite layer over these silicon bottom cells. Moving on. Uh, Kelvin force probe microscopy was employed to measure the effects of the textured surface of the electric field by comparing it with the electric field across the flat surface. It was observed that the perovskite layer electron transport layer interfaces had similar electric field strength and depletion widths for both flat as well as textured surfaces, but the electric field significantly increased for a textured layer across the whole transport layer perovskite interface as compared to that of a flat surface. The depletion width across the whole transport layer electron junction for a textured substrate varied with the thickness of the perovskite layer over the silicon pyramids. The valley region had a wider depletion region and hence a greater perovskite layer thickness as compared to the peak region, suggesting better charge collection and electric field superimposition at the peak pyramid valleys. This beneficial geometrical factor was observed only in the case of solution process cells and not in other PVD processes or control mechanisms. Uh, the EQE reports, also referred to as the external quantum efficiency reports, highlighted the increased short circuit current density in both the top and bottom cells of the fully textured device, suggesting a greater device performance for fully textured cell as compared to a flat perovskite cell. Moving on to conclusion, these solution process tandem cells created by her and his colleagues had a remarkable efficiency of 25.7%, coupled with high thermal stability. It also exhibited low hysteresis loss and excellent stability under accelerated optical tests. It also had an outstanding operating lifetime, which could be attributed to the incorporation of inorganic NIX materials, which successfully averted iodine reactions with small organic molecules, which significantly reduced the device performance and operating lifetime. It also had extremely low reflection and current density losses and achieved current matching between individual cells by widening the band gap of the perovskite layers. Even though efficiency and device performance characteristics have been comparable to that of other solution process cells, exhaustive research is paramount to achieving commercialized tandem solar cells for industrial applications. So moving to references, here are some of the research papers which helped us make this presentation. So here is our contribution for your reference. Thank you.